Hey there, everybody. Thanks for coming back today. Recently, we looked at taking derivatives using the chain rule, and that's going to lead us right into our next topic here, which is called implicit differentiation. Okay? So first of all, what does implicit differentiation mean? Let's take a look at explicit versus implicit. Up to this point, you've learned how to differentiate functions that are expressed in an explicit form. Now we're going to take a look at relations written in an implicit form. Let's take a look at the difference in the two types of functions. So explicit, y equals x squared plus 1. F of x equals root 4x cubed minus 2x plus 1. Those are explicit functions. Implicit, written equations. X squared minus 2y cubed plus 4y equals 2. Xy minus 2x squared plus y cubed equals x plus y. What are the difference between the two? Okay. In the explicit ones, we have an input, and then we get an output. Right? We put x in, we put a number in for x, and we get an output y back. Not necessarily true for implicit here. Okay, they can't necessarily solve these for y. Sometimes we can, sometimes we can't solve these for y, but many times we can't solve these for y. We talked about this a couple weeks ago, but let's go back to that where we're differentiating with respect to a variable. In this case, we're going to differentiate all these with respect to x. Okay, so for example, the first one, the derivative of x cubed is 3x squared dx, but with respect to x dx. Now remember, dx over dx is 1, so we don't have to write that. And we haven't been writing that in our derivatives recently, so we just use 3x squared. That's our answer for question A. What happens when we change it to y cubed? All right, well, the derivative of y cubed is still 3y squared, but this time it's dy. And since we're differentiating with respect to x, it's dy dx. And dy dx is not 1, usually, so we do have to write it. So our answer here would be 3y squared dy dx. And about the derivative of x plus y. Right? The derivative of x plus y. So the derivative of x is just 1 dx dx, and the derivative of y is 1 dy dx. So we can simplify that to 1 plus dy dx. And here we have our last one on this slide, xy squared. X times y squared. That's going to give us a product, so this is going to be a product rule problem. So the product rule, remember, is the first function times the derivative of the second function. So the derivative of y squared would be 2y dy dx, plus the second function times the derivative of the first function, derivative of x would be 1. Clean this up a little bit, we get 2xy dy dx plus y squared. So you can see how when we're taking derivatives of a different variable with respect to x, we can't just ignore the dx part because it's not going to be 1. So there are some guidelines. When after you see a function is, sorry, not a function, but an equation is written implicitly, you want to start by differentiating both sides of the equation with respect to x, unless told differently. Collect all terms involving dy dx on one side. The left is usually the good side to do that too. And everything else to the right side. Factor dy dx out, and then solve for dy dx by dividing. So let's take a look at that, how that works. So we have the derivative of this would be 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x dx dx, which we don't have to write since it's 1, equals 0. So then we'd want to keep all this, since they all have dy dx's together, but the 2x does not, so we're going to add that to the other side. Then we're going to factor out dy dx and what's left. And then finally, to get dy dx by itself, we have 2x over 3y squared plus 2y minus 5. The next one here has the equation x squared plus 4y squared equals 4. Hopefully you remember that from your Algebra 2 or pre-calculus days. That's just going to be an ellipse. If we were to sketch that here, well, first thing we should probably do is divide everything by 4. We get x squared over 4 plus y squared over 1 equals 1, right? So we're going to go left and right 2 units to square root of 4, and up and down 1 unit to square root of 1. And there's your ellipse. That's not an ellipse. There's an ellipse. So the question says to find the derivative of the equation above. All right, so let's take the derivative of that. We would get 2x plus 4 times 2y dy dx, so 8y dy dx equals 0. Solving for dy dx, we can subtract the 2x over to the other side and divide by 8y. We get negative x over 4y. And there's our derivative at any point on that ellipse. Find the slope of the tangent line to the curve at the point given. All right, so we're just going to take that point that we got and put that into dy dx. So dy dx at the point root 2 comma negative 1 over root 2 is negative root 2 over 4 times negative 1 over root 2. So that's negative root 2 over negative 4 over root 2. And if you flip and multiply that, negative over negative will cancel to a positive. We would get root 2 times root 2 over 4, which is 2 over 4 or 1/2. Okay, then for C, easy now to do this. Our tangent line would be y plus 1 over root 2 equals 1/2 x minus root 2. And then E says write the equation above explicitly and take its derivative explicitly and compare the results with part B. All right. So we're going to take this equation, x squared plus 4y squared plus 4. And we're going to take the derivative, we'll solve that for y and then take the derivative of that. So if we solve this for y, we would get 4y squared equals 4 minus x squared. So y squared equals 1 minus x squared over 4. So y equals plus or minus the square root of 1 minus x squared over 4. So we're going to take the derivative of that. I prime or dy dx. Remember, this is like saying 1 minus x squared over 4 to the 1/2, right? So that'd be 1/2 times 1 minus x squared over 4 to the negative 1/2. And then using chain rule, the derivative of the inside would be 0 minus 2x over 4. So it'd be negative x over 2. So if we simplify this a little bit here, we would get negative x over 4 times the square root of 1 minus x squared over 4. If we put root 2 in for x here, the whole point of this is that we should get the same answer back. Okay, so if you put root 2 in for x here and here, we should get the same slope that we got before, which was 1/2. Okay? Sometimes it's easier to do these problems like we did part E. Sometimes it's easier to do these problems like we did part B. Okay, this problem obviously is much easier to do the way we did part B. Okay, but sometimes if it's really easy to solve for that, solve for y, then you can go ahead and do it that way and then take the derivative explicitly like we've been doing. Okay, let's take a look at another example here. So we have the relation sketched using Desmos on the right side over there. It says find the slope of the graph of that relation at the point 3, 1. Okay? Here's your relation here. The first thing I'm going to do is I'm going to divide that by 3. Divide both sides by 3, just to clean up the left side, because that already looks like it's complicated enough. You don't need to do this. This is just personal preference here. All right. So the derivative of the left side is chain rule. 2 x squared plus y squared to the first times 2x plus 2y dy dx. That's the derivative of the left side. Equals 100 over 3 times, and then this is going to be a product rule, x times the derivative of y plus y times the derivative of x. All right, now our goal is to get dy dx by itself. Okay? Let's clean this up. So I'm going to start here by distributing the 2 in here. Now we get 2x squared plus 2y squared, and then 2x plus 2y dy dx. And if I distribute the 100 over 3, so I get 100 over 3 x dy dx plus 100 over 3 y. All right, at this point, let's stop and look at what the question is actually asking us to do. It's not actually asking us to find the derivative. So do we need to solve this for dy dx? Right now, we do not. And that's a good thing, because this looks like a pretty complicated equation to solve for dy dx. Okay, we'd have to do some distributing over here, and then get all the dy dx's together, and then solve for that. But the question's not asking us to do that. It's simply asking for the derivative at one point. So instead of doing all that work, we can just take that point 3, 1 and put it in right now and find our slope. So we would get 2 times 9 plus 2 times 1 times 2 times 3 plus 2 times 1 dy dx equals 100 over 3 times 3 dy dx plus 100 over 3 times 1. This is going to be much easier to do with numbers here. Much easier to clean up with numbers. All right, so this first part gives us 18 plus 2, which is 20. The second part gives us 6 plus 2 dy dx equals 100 dy dx plus 100 over 3. And then just keep simplifying here. Right side's not going to change yet. And now we can say, all right, let's get our dy dx's together on one side. So I'm going to subtract 40 dy dx from both sides. and I get 60 dy dx. And then if I subtract 100 over 3 from both sides, getting a common denominator, this would be 360 over 3. So 360 over 3 minus 100 over 3, that would be 260 over 3. And dividing by 60, I get dy dx would equal 260 over 180, or 26 over 18, or 13 over 9. So the slope at the point 3, 1 is right here. The slope of that tangent line at that point would be 13 over 9. So a little bit bigger than 1. Not quite 2, but a little bit bigger than 1. Okay, the last thing we're going to talk about on this section here is an optional topic. It's not usually covered on the AP test, but it's a really neat and unique type of way of solving some derivatives, finding some derivatives of functions. Okay, so pause the video right now, take a look at example 5, and just see how many of those derivatives you can take with our current knowledge. Hopefully, you came back and said you could do 3 of them right now, right? The first one is just a constant. E to the e is a constant, so the derivative of that would just be 0. The second one, we know that one, e to the x, is just e to the x. The third one may not look like it, but we're just using the power rule here. E is just a number, remember? So it's just e x to the e minus 1. The fourth one, however, we cannot do. Okay, and that requires what's called logarithmic differentiation. And as you can see there, part D above is problematic for us using the rules that we know. When a variable appears in both numerator and denominator, we must use what's called logarithmic differentiation. So here's a problem where we have to use logarithmic differentiation. Y equals x to the 2x. You can see there's a variable in both the base and the exponent, right? So how do you use logarithmic differentiation? What you're going to do to start here is you're going to take the natural log of both sides. All right, and using a rule that you learned back in Algebra 2, then allows us to bring down the 2x out in front of the ln x. All right, now if we take the derivative of both sides, the derivative of the left side would be 1 over y dy dx. On the right side, we have a product rule. So 2x times 1 over x plus ln x times 2. Okay. Multiply both sides by y, and we get dy dx equals y times, now I'm going to clean this up a little bit, 2x over times 1 over x is 2 plus 2 ln x. All right, and what is y? Well, y is x to the 2x. So I can write my final answer here as x to the 2x times 2 plus 2 ln x. Not too bad. So something to think about here. We already have learned how to take the derivative of y equals 2 to the x. But what if we didn't know that formula? Well, let's try using it. Let's try taking the derivative the way we just learned, using logarithmic differentiation. So ln y equals ln 2 to the x. So ln y equals x ln 2. So that's 1 over y dy dx. And the derivative of the right side, that's just ln 2, which is a constant, times x. So that's just ln 2. Multiply both sides by y. You get ln 2 times y. And y is 2 to the x. So our final answer here would be ln 2 times 2 to the x, which is the formula we've already learned for taking derivatives that look like that. Okay, so the last one here. Man, that looks pretty difficult, huh? And we could make this very difficult on ourselves. We could do a quotient rule that involves double chain rule. Okay, and it will work. You'll get the right answer. But why do that when we just learned this great technique where we can take the natural log of both sides? Why would I do that? It makes it look worse, right? Now that we know our log rules that we learned in Algebra 2, I can rewrite the whole right side to look like that, right? Your exponent can come out in front. And remember, this is an exponent of 1/2, and that can come out of front. And we can separate this into two separate logs. And now the right side's derivative is going to be so much easier to take. The left side, we have 1 over y dy dx. The right side, we have 2 times 1 over x minus 2 times 1. So we don't have to write that. Minus 1/2 times 1 over x squared plus 1 times 2x. And if I multiply both sides by y, I get 2 times x over x minus 2, 2 over x minus 2, minus, these 2's cancel, so x over x squared plus 1 times y. And what is y? X minus 2 squared over root x squared plus 1. And all in all, not that difficult a derivative to do using logarithmic differentiation. If we tried to do that derivative using a quotient rule with 2 chain rules involved in it, it'd be very complicated. It would work. We would probably get a different looking answer, but it would be equivalent to the answer we got. Okay? That's it for our lesson on implicit differentiation. Thanks again for checking in today, and I hope to see you again soon.